Another thing that we can talk about, now that we know how to write lines in space, we can talk about whether or not a pair of lines are equal, meaning they share the same exact set of points. They're parallel, but not equal. That's where they're parallel. They have the same direction, but they do not have any points in common. Or if they're skew, where they're not parallel, they have different directions, but they also never intersect each other. Or the last categorization, which is whether or not the lines intersect. So again, now that we know how to represent lines in space, we can classify pairs of lines as equal, parallel but not equal, skew, or intersecting. So we're going to take a look at a pair of lines here and determine whether or not these lines are, well, we're going to classify them as one of those four classifications. So we have line 1 and we have line 2. Line 1 is written in parametric equation format, and I don't love this format. I've used it because I know that our textbook formats some of our equations like this. So here's the x equation for line 1. I'm going to copy it down and write it vertically. And then we have the y equation from line 1. And then we have the z equation from line 1. To me, that's just a lot easier to read, and so I'll do the same thing for line 2. And I'll take a second to address a common misunderstanding. Line 1 has the parameter s. Line 2 has the parameter t. The reason why we're using different letters for these parameters is to distinguish that we're plugging in different values to generate points. It's possible that s and t can be equal, that's fine, but we just want to highlight that they don't have to be equal, and that's why we're using a different letter. So if we're looking at these two lines, then we can extract the point P0 from each line. So let's go ahead and do that. From line 1, P0, and we'll color code these, why not? Used blue. From line 1, P0 comes from the constant in our equations. So P0 is at -1, -1, -4. And then for line 2, we again are extracting the constants. So we have -3, 8, and +5. Now you have to really focus on the fact that these equations can be written with small variations. What I mean by that is sometimes the constant appears first, and then the parameter with the coefficient is second. And sometimes the parameter with coefficient appears first, and the constant is second. The only way to know which number applies to the point is to pick out the numbers that don't have the parameter at all. So the constant terms tell you the coordinates of the point. The coefficients on the parameters, those tell us the values for the parallel vector, v. So for line 1, the parallel vector v looks like 2, 1, 1. I just pulled the coefficients off of the parameter terms. And then for line 2, the vector v would need to be 1, 3, -2. Now that I have those things, we can start to talk about whether or not the lines are equal, parallel but not equal, skew, or intersecting. If these lines are parallel, then the vectors have to be parallel. I'll call this v1 for the vector from line 1 and v2, the vector from line 2. So if the lines are parallel, then v1 has to be parallel to v2. They have to have that same direction vector. So we want to know, are they parallel? We have to check that. So we're going to check to see if our vectors are parallel by inspecting whether or not they're scalar multiples. The vector v1 has components 2, 1, 1. The vector v2 has components 1, 3, -2. Now I want to look at the corresponding components and figure out, is there one scalar that I can multiply to make the corresponding components match? Now looking at the x components, I would maybe suspect that that scalar has to be 2. But then if I look at the y components, or those second components, I can see that the scalar 2 doesn't work there. And it doesn't work for the third components either. In fact, there's not a number that I can multiply to v1 so that it's equal to v2. Or vice versa, there's not a number that I can multiply to v2 to make it look like v1. So they're not parallel. They're not parallel because they're not scalar multiples. So v1 is not a scalar multiple of v2. When you're asked to justify why two lines are not parallel, this is a great way to do it. You could calculate the angle between the two vectors and find out if you get 0 or 180, but this is much faster. Check to see if the two vectors are in fact scalar multiples, and if they're not, then they can't be parallel. So we know that they're not parallel, and if they're not parallel, then they absolutely are not equal. So we have two possibilities. Either they're skew, they never intersect, or they do intersect. And this can be quite a bit of work. If they are skew, then we have to prove that they never intersect, meaning there's never a parameter that I can pick for s and a value that I can pick for t so that I generate the same point on either line 1 and line 2. If they are intersecting, I should be able to find the parameter value for s and t that would give me the same point on the line. So we're going to try and solve this system of equations. We need all the equations from L1 and all the equations from L2 and we want to solve this for s and t. Essentially, we're trying to solve for s and t because we're looking to see if a point x, y, z exists that matches both line 1 and line 2. Because we have two equations that are equal to x, I can set them equal to each other and make one new equation. So I'll have 2s minus 1 equals t minus 3. And I can do the same thing for the y equations, setting those equal. I have s minus 1 equals 3t plus 8. And then for the z equations, I have s minus 4 equals 5 minus 2t. I have two unknowns. I have three equations. I want to solve this system for s and t. One thing that we can do is substitution. We could also try elimination if we want. In fact, there are quite a few different tools that we can use to find the solution to this system. I'm really not picky on which one you use. I just want you to make sure that you solve the system correctly. So I'm going to use substitution. What I'm going to do is take this first equation that I have in purple, and I'm going to solve that for t. So I'll add 3 to both sides so that I get t is equal to 2s plus 2. And then I'm going to substitute that in to the second equation. So plugging that in, I would have s minus 1 equals 3 times t, but I'm going to use 2s plus 2 instead of t, and then add 8 to it. And then we're going to simplify this the best we can. So we have s minus 1 is equal to 6 times s plus 14. Let's get all of the s's on one side. So I'll have 5s is equal to negative 15. That tells me that s should be equal to negative 3. But if I were to, instead of plugging that t substitution into the second equation, if I instead plug it into the third equation, I accidentally erased everything. So we're going to pick up where we left off. I'm going to write out my system of equations again. And I'm going to remind you that we solved the first equation for t, so that we had 2s plus 2 for t. And when we substituted t into the second equation, we found that s had to be 3, or negative 3, I believe. But what I'm saying is we need to check that that same s value works when we substitute that expression for t into the third equation. So let's go ahead and do that. We have s minus 4 equals 5 minus 2 times t, but instead of t, I'll plug in 2s plus 2, and then we'll simplify. So I have s minus 4 equals 1 minus 4s. I want all my s's on the same side. And this is telling me that s needs to be 1. What that says is that the s value is not consistent throughout this entire system. The first two equations were solved with s being negative 3. The second two equations, those were solved with x equals 1. This is an inconsistent system. Because we can't find one s value that will solve all three of these equations that we've created with our lines, we know that this has no solution. The system has no solution because we got two separate answers for s, and we're only allowed to have one answer for s, one answer for t. So this system has no solution, which means these lines never intersect. They don't have any points in common. And I've created a little animation so that we can see that, in fact, these lines are not intersecting lines. It's kind of hard to see here, but we can see that we have the point P that was given to us and the line, and there's a little parallel vector there, and then the point Q that was given to us and the line and the little purple vector that's parallel there, and that these lines do not intersect as we see them. And if I allow that animation to play, we can see that in fact those points are not, those lines are not intersecting. There's space between them. So these are skew lines. They're not equal, they're definitely not parallel, they don't intersect, therefore they have to be skew. All right, let's try another set of lines. Again, trying to classify as equal, parallel, but not equal, skew, or intersecting. Very first thing that we need to do is pull out the information from line 1. So from line 1, I need to know the point P. And line 1 is written in the symmetric equation form. And from that, we can tell that the coordinates of the point P have to be at 0, 0, 0. And if you're not sure about that, pull up the symmetric equation formula again and plug in x0, y0, z0, plug 0 in for all of those, and you'll see that you just have x, y, z in your numerators. From line 2, the point that we're given has the x coordinate 3, y-coordinate would have to be 0, and the z-coordinate would have to be 2. The vectors v from line 1, that first part of the equality is just x, which if I pretended there was a denominator there, it would have to be a 1 on bottom. So I have 1 for the component in the x position for v. The middle part of our equality has negative y, and the only way for that to have happened is if there was a negative 1 in the denominator, and then it was just written as negative y rather than y over negative 1. So I know that the second component is negative 1. And then for z, I would have to have a positive 1. For v2, I have a 2 in the denominator for that first component, so I know the x component of v2 is 2. My y part of the equality is positive, so that would give me a positive 1, and then the z, I could imagine that there was a 1 underneath that as well. If you're not really sure that what I've pulled out for p and what I've pulled out for v on each line is true, try creating the symmetric equations of a line using these p and v values and see that you come up with the lines that we started with. Okay, the reason why we went through that process of extracting all that information is so that we can check to see if the vectors are parallel. If they're parallel, then we might have equal lines, or we might have parallel but not equal. So let's check those first. If they're parallel, v1 and v2 have to be scalar multiples, so let's check to see if they are. If v1 and v2 are scalar multiples of each other, then I can find a single number to plug in for k so that this equation is true. I don't think I can find any number k that will make this work, especially because I can see a negative on the left-hand side and there's no negatives on the right-hand side. So we don't have anything that would make that work, which means definitely not equal, definitely not even parallel. So we know we're looking at another set of skew or intersecting lines. Just like last time, we're going to create a system of equations using the equations from the line. And to do that, with equations, symmetric equations, we have to create those equations first. So right now, line 1 is expressed as one equation. We're going to break it down into 3 by remembering that that was equal to a parameter. I'll pick the parameter to be r. So then I have the 3 equations: x equals r, negative y equals r, and z equals r. And then for line 2, I'm going to set that equal to a parameter because that's the definition of symmetric equation. And I'll pick s instead of r. So then I'll have x minus 3 over 2 is equal to s. I'll have y is equal to s. And then I'll have z minus 2 is equal to s. So this is the system that we're solving for s and r. Or we can say we're solving for s and r with the intention of finding the coordinates of the point x, y, z. So if we suspect they're intersecting, then we should be able to find that point, x, y, z, where they intersect. So there's really 2 goals that are identical. You just go in different paths to get there. Either you solve this system for s and for r to find what we need to plug into our 2 line equations to find the point, or we solve the system for x, y, z. Whatever feels easier for you, do that, but know that it's not really important to know all 5 of these quantities. We just need to know, is there a point that exists? And we can answer that in one of 2 ways. We can find s and r, or we can find that intersection point x, y, z. So let's just start with what we can do easily and see where it goes from there. I'm looking at these 2 y equations and saying to myself, those have probably got to be the easiest equations for us to work with. So I'm going to start there. I see that we have r equals negative y equals positive s. So we could rewrite that as y equals negative r and y equals s. In other words, negative r is equal to s. And then we can go through and replace all of our s's with negative r's. So this would be negative r, negative r, negative r. And then we can rewrite our system. X equals r. I also have x minus 3 divided by 2 equals negative r. And then we have equals r, and z minus 2 equals negative r. I'm skipping that center equation because we've used it. So if we use this, then the result is the following four really sets of equations. And now we can start to work these against each other. So if I take the first two equations that have x in them, I can write that x is equal to negative x minus 3 over 2, and then solve for that. So that would be 2x equals 3 minus x, which would give me 3x equals 3, or x equals 1. So we're kind of juggling here. We don't know what r and s have to be, but we would have to find x equals 1 so far. We'll try our second set of lines here. If z equals r and z minus 2 equals negative r, then z would have to equal 2 minus z. And if I add z to both sides, I get 2z equals 2. In other words, I get x equals 1. Not x equals 1. Z, we're solving that one for z. So we just found that z had to be equal to 1. Now we just need the y value. So if we know what x is, then we know what r is, because x is equal to r. So if x is 1, r is 1. And we know that y is equal to negative r, so r would have to be 1, and then y would be negative 1. Solving systems is really like a juggling act, and you probably learned how to do this years ago, and maybe you haven't used it very often since. I highly recommend spending some time practicing solving systems because it's really tiny mathematical steps, but the trick to solving systems is to be able to step back and look at what you know and what you're trying to learn, what you're trying to solve for, and working your way in that direction. So you don't want to do this huge circle or work backwards. You want to work towards the thing you're looking for. And that's exactly what we just did right now. We found the point of intersection, and we indirectly used the values of s and r to get there. And we could even go back and say what s and r would have to be. If x is equal to 1 and x is equal to r, then r has to be equal to 1. And if negative r is equal to s, then s has to be negative 1. So it's not super important to know what these parameters are. We just either need this or we need that intersection point. So we're using 6 equations against each other, and we're hoping to either find r and s or to find x, y, and z. Now, because we were able to find r and s, or in other words, we were able to find that intersection point, we know these lines are not skew. They have to be intersecting because we found where they intersect. And I made another little animation here to show you what's going on. So I have the purple line and the orange line, and I've marked the point of intersection for you. And we can see that these points, these lines share that common point. We can also see the vectors that go with each of the lines. So remember that from the first equation, line 1, we extracted the point at the origin, and we extracted the vector that was on the line. 1, -1, +1, and we can see that vector right here. And then from line 2, we extracted the point 3, 0, 2, which I have up here labeled Q, and the vector 2, 1, 1, which is what we have here in purple. And so we're able to see each of the lines defined by their point and their parallel vector, and we're able to see that intersection point that we found, the red point in this image. We have another set of lines to look at. Again, we want to find out if they're equal, parallel, skew, or intersecting. So we start by extracting the information that we have from each line. From line 1, the point that I can see on the line comes from the constants in the parametric equations. So I have a -1 constant. In the y equation, there is not a constant, so there would have been a 0 in there. From the z equation, we have a +1, which really means that we have a negative value for that. So our p is at -1, 0, +1, 0, -1. And then for the vector v from line 1, it's coming from the coefficients on all of the parameter terms. So 6, -2, and 3. Now let's extract everything we know from line 2. The point P comes from the constants in the numerators. Remember, the minuses are built into symmetric equations, so our point P has coordinates 4, -3, +1, and then the vector that our line 2 is parallel to comes from the numbers in the denominator. So we have +6, -2, +3. We want to check to see if these vectors are parallel. If they are, then we can find a scalar such that when we set up the vectors to be equal to each other, multiplying by some number k will make these two vectors equal. Well, guess what? This one's super easy. K would just have to be equal to 1 because these vectors are parallel to each other. They're identical vectors. So now we just need to check, are they parallel or are they equal? If they're equal, then they share common points. If they're parallel but not equal, then they do not share any common points. So we're looking at one of these two options. We know they're not skew or intersecting because the vectors v1 and v2 are parallel to each other. To find out if they have any points in common, we need to create that system of equations. So from line 1, and then from line 2, we need to set those equal to a parameter. I'll use t. And then we want to solve this system to find out if there's any points in common. Play with it. See what you can do. See if you can find any values for s and for t that will make this true. Maybe it would be helpful to rewrite these expressions solved from line 2, solved for x, y, and z. And if we take a look here, if I pick t to be a certain number from line 2, and I pick s to be a certain number from line 1, unfortunately, there's not a number that I can pick to make these equations identical. So looking at the 3 that we get from line 1, the 3 that we get from line 2, the constants don't match, which means these don't share the same points. Even if we were to play with the values of the parameter, they won't share the same points, which means these lines are not equal. They are parallel, but they're not equal. And of course, I made a little picture for us to look at with the two lines. We can see in this picture that the vector v1 and v2 are overlapping. So I made them dashed lines so that you could see both colors there. We can see the initial point P for one of our lines and the initial point Q for the other line. And we can see that these two lines are definitely parallel, but they don't have any points in common, so we know that they are definitely not equal. So parallel but not equal.